So we're starting the last session. John is going to talk about cloud-based data services, and after that we will do a little bit of cleanup. So if you see anything lying around, just take it with you or throw it here in the garbage bin. Thank you, John, for the talk now.
Cheers. So thanks for the invitation. So today I'm going to talk about building cloud-based data services to enable earth science workflows across HPC Centres. I'm based at ECMWF, and this is part of a project which is funded by Horizon 2020 called HiDALGO. So an overview of what I'll talk about. I'll give a brief introduction to ECMWF, who we are and what we do. I'll talk about the data challenge that we're currently facing and ways that we want to mitigate that. And then I'll talk about HiDALGO and ECMWF's role in HiDALGO and what that means. So ECMWF stands for the European Centre for Medium Range Weather Forecasts. It was established in 1975. It's an intergovernmental organization, and it's also an NWP, or Numerical Weather Prediction Operational Centre. So I'll talk a little bit about what that means in a moment. It also supports then national weather services through its output. It's also a research institute, and we also have Copernicus services. We run 2 Copernicus services, C3S and CAMS, and we also support then an additional service called CHEMS. We're based in Reading in the UK. And we're currently finalizing our new data center in Bologna in Italy. Our HPC is currently located in our center in Reading, but it will move. So our new HPC will be installed in Bologna this year, and we hope to have that operational by next year. So who are we and what do we do? As the name suggests, medium range weather forecasting is our core focus, and we're an operational center for that. So that means that we run a global high resolution model, so between 9 kilometers and 18 kilometers, depending if it's ensemble or high-res, on a production schedule of 6 to 12 hours. Medium range, in this case, for weather forecast means between up to day 10 and up to day 15. And then we also do slightly longer timescale weather forecasts of on monthly and seasonal timescales. What we don't do are short-range weather forecasts. So this is what you'll be familiar with from your own national weather services. They focus on those, and that's their area of expertise. They're usually running on downscaled, very high-resolution regional models and on a much higher, more frequent production schedule. But the output of our global model uses the input for a lot of these regional models, at least within Europe. And what we also don't do then is climate prediction, CO2 doubling, and so on. This is rather for research. So as I mentioned, we have a time-critical component. So twice per day, we have 2 main runs at 0 and 12 UTC. We have a HRES, which is a high-resolution run at 9 kilometer resolution, and we have an ensemble resolution, which is run at 18 kilometers. We're producing about 100 terabytes per day at the moment from those model runs, and we have about 85 million products, and we also have real-time dissemination then to many destinations worldwide. We have non-time critical components, so we have also research within the center, which is looking at continuously then updating and improving the model. And finally, we have the largest meteorological archive of its type in the world. So it's currently in excess of 300 petabytes. We have 5,000 plus daily active users of that archive, and we're adding at the moment about 250 terabytes per day, and that's accelerating. Our facility, so at the moment we have 2 Cray HPCs. They're identical for redundancy purposes, so that if anything happens during the production of a run with one HPC, we can relatively easily switch to the second as a backup. At the same time, we're also utilizing the 2 as much as we can for research and for other purposes. They're currently in the top 50 globally. We also have cloud services, which we've just started building up in the last few years. So we have something called the CDS, which is the Copernicus Data Storage. It's operational about 2 years or so. We have the European Weather Cloud, which is a pilot, which we're currently setting up with EUMETSAT. And we also have Wikio, which is a collaboration with MacArthur. And again, the archive that I just mentioned, it's primarily on tape drives, 140 tape drives, and we're adding, as I said, 100 terabytes from the operational side, 150 other, and that's 250 total at the moment. So that's leading us then to the data challenge. So you might have seen this slide possibly before, particularly throughout my colleague's presentation earlier on in the day. But if we look at the disseminated data that we're disseminating globally to these 200 destinations per day, as recently as 2015, 2016, this was the order of about 5 terabytes. And we're now up to 30-ish, and this is only going to grow further. So getting kind of near to what currently we can push out. And also our model output, our ensemble is currently running at 18-kilometer resolution, which is the first bar here on the second chart. And that's responsible then for about 70 plus terabytes of data per day. This is projected to grow to 900 plus terabytes, or the petabyte range, by 2025 for 5-kilometer resolution. And that's only the beginning of what we're looking to do. So we're looking to go to 1.25, 2.5 by 2030 in 10 years. So that number will be higher again. So we are facing quite significant challenges in terms of data growth. What's driving that? So there's three kind of main axes that we can think about when we consider what's really driving that exponential data growth. So first of all, we have reliability. So historically speaking, weather forecasts were run purely in deterministic mode. So you would have a weather forecast model, NWP model, you'd let it run for some period of time, and then that was your forecast. And obviously that wasn't didn't give you an idea of the probabilistic sense of that forecast. So ECMWF were pioneers in setting up the idea of an ensemble forecasting system about 30 or so years ago. And this is where you take your initial conditions that high-res model runs in, you slightly perturb them. In our case, then we have 50 ensemble members. So each one of these ensemble members then runs a perturbed initial condition, and we let that evolve forward then, and then we do statistics on those forecasts then and come up with a more probabilistic type of a weather forecast. We're also then, another axis that we can consider is model resolution, naturally. So depending on HPC resources that we have access to, we're continuously trying to push model resolution to higher and higher resolution so that we can resolve cloud convective processes better, cloud processes physics better, and so on. And then finally, there's the complexity of the model itself. So traditionally speaking, we were just dealing with atmospheric models, so just modeling the atmosphere with what we call the IFS model. Nowadays, you have a whole Earth system model. So you have an ocean, you've coupled that with an ocean model, you have to model ice, land use, and it gets more and more complex as time goes on. And then the interaction, or all these three components combined together, are essentially fueling this rapid exponential growth in data. So what is the problem? The problem is that no user can really handle all that data in real time as we produce it. Much, unfortunately, of our ensemble forecast data goes unused. So we're continuously looking for ways of trying to encourage users to use more and more of that data, but it's becoming more of a challenge. And it's particularly not made easy by domain-specific formats and conventions. As I mentioned, we're disseminating, pushing 30 terabytes at the moment globally to destinations across the world, which is going to be a challenge as we start looking towards those projections that we were looking at a moment ago. And then web services. So we're developing and exploring web services then to allow users to access data. So the key challenge here is how can we improve user access to such large volumes of data? So how can you actually access it today? Well, today we have something called ECMWF Web API that allows users to come and access Mars or the public data sets depending on what permissions they have. So authorized users and commercial users can access the Mars archive. So Mars here is the meteorological archive that I mentioned a moment ago. For public access, we currently have public data sets available, so you just simply have to sign just a general license agreement and you can then self-register and access that data. In order to access it, you use the ECMWF Web API, which you can access here, and we encourage you to go to those links and check them out and use the data and start exploring the data if you're interested in doing so. We have a retrieval example here where you would specify in meteorologically meaningful parameters. You would specify precisely what data you're interested in retrieving, and then you retrieve it in formats like netcdf, grib, JSON. At the moment, we do differentiate here between public access and private access, or commercial access, let's say. The public access at the moment is for a limited set of data sets, but we have recently, our council has recently decided to make all our data open by 2025. So in the next 5 years, we'll gradually phase more and more data from the commercial side into being publicly available. At the moment, what's primarily in the public data set is climate reanalysis or historical climate data, you could say. For example, like ERA 5, ERA Interim, ERA 40, if you're familiar with those data sets. And over time, for example, this year we'll release EC charts. They will be publicly available by the end of 2020. And in the coming 5 years, we will essentially make all of our data open access. Another way you can access data today is through the CDS, or Climate Data Store. This was a portal that we introduced and built about 2 years ago to allow users to come and search for what data we have and then to download it and to start playing with it. So one issue that we face with such large volumes of data and growing volumes of data is that our data sets are becoming quite large for users to work with locally. So it's quite challenging for users to download all that data on a global level, let's say. Then they have to also have the required processing power then to process that locally and to transform it or whatever they're interested in doing on the client side. So what we've done here is we tried to migrate some of that processing rather to the server side, and you can do this with Python interface, and allows non-domain users then to build apps and to build on top of that. So what's primarily in the CDS at the moment is reanalysis data. For example, the Era 5 new data reanalysis data set that we produced a couple of years ago is available there. So if you're interested in that data set, you can go check that out. And there's also a link where you can register today and register right now and start playing with it. So we are thinking about then novel data flows. So the way our data flows have worked historically and the way they're still working today is that we have our HPC. It's running then twice per day, as we mentioned, in terms of our main runs, and it's then producing weather forecast data. And then we have our FDB, which is our dedicated object store for meteorological data. So that's basically where we store the data immediately after production. And then we have the PFS, which is Luster. And then we archive data then. Everything we produce and everything that has historically been produced at the center is archived. And that's our Mars archive combination between disk and tape. And so the new kind of model or paradigm that we're introducing then is the cloud-based paradigm. So rather than taking all these large volumes of data and moving them out of the center and then making users, first of all, store that data and then try and process it, we want to rather move the users to the data. And we also want to do that while the data is still hot, so to speak, and with scientifically meaningful metadata. What we mean by hot here is that our forecasts are really only meaningful within a certain window of time. I mean, they can be meaningful for research and for other purposes later, but obviously a weather forecast has a sort of a limited shelf life. And we want to get users to the data as quickly as possible so that they can actually utilize that within a short time frame that after it's been produced. So HiDALGO and ECMWF. So HiDALGO is the project that I'm funded on. It's a Horizon 2020 project, which is a HPC and big data technology for global systems. It's a collaboration across 13 institutes across 7 countries. The mission is to advance technology to master global challenges. And the mission then is to develop novel methods for HPC, HPD, and so on to simulate the complex processes involved with those global challenges. And also then our role in this will be to couple data and couple particularly weather data for certain pilots. So we have 3 pilot test cases. We have a human migration pilot from a group at Brunel University, an air pollution pilot from a group at SZE in Hungary, and a social networks pilot from Plus in Austria. And of these 3 pilot test cases, 2 pilots in particular are of interest for us, as they will couple with our weather and climate data. So weather and climate data can we consider potentially useful input for migration models and also for air pollution models. So ECMWF's role will hopefully be to enable coupling as a means to build a workflow. So what we mean here is that you can consider the HPC, in our case, which is actually a closed HPC. So for the purposes of HiDALGO, because we are an operational center, we can't simply give users access to the HPC and let them play it and break it and so on. So rather, we can, through the cloud, give users access to the output of the HPC. So what we are going to do here is we'll have co-located private cloud at ECMWF with the HPC. This will then give users access to what would then be, prior would have been a closed HPC. And from that then they can build a workflow starting from our forecast output. Via the cloud, they can then do some processing on that data to prepare it for their own simulation. That simulation can then run in a HPC, high performance compute environment, and then they can then post-process the data afterwards or visualize and so on. So the key point here is that we kind of want to open up a closed HPC system and bring valuable experience in integrating such a closed HPC system with such workflows. We think this could be a useful model for other HPC systems around Europe who have similar restrictions to us in terms of operations and in terms of access. We have 2 HPC centres that we will be collaborating with, so that's HLRS, Hazelhen in Stuttgart, and Poznań, the Eagle supercomputer, and then our own cloud resources will then feed into that as well. So we look to try and couple data. So there's 2 steps to coupling that we're envisioning. So first of all is static coupling. So because these models that we want to couple the weather and climate data with, they haven't previously taken account of such data. So the first stage of the project is for them to take the static reanalysis data, historical data, to analyze that and to see how maybe have used to integrate and improve their own simulations, like the human migration, for example. We've already completed that, and we've done that using the CDS. And then there's dynamic coupling. So from year 2 onwards, or from 2020, we want to couple forecast data. So while it's hot, while the hot data we were talking about, we want to couple that via REST API. And again, this is the model of bringing the users to the data while the data is hot and meaningful, and to enable them to build custom workflows utilizing our data. This is sort of just reiterating kind of the points. The models we have already are the push, where we disseminate data over the internet, the pull, where users can come and get our data through the archive, and the third model that we're producing now is the cloud model, and the idea here is to move the computer, not the data. So in order to do that, we need to build a cloud data as a service, which we've named here Polytope, and this is basically under development at ECMWF. It will be deployed to ECMWF, but accessible externally, and we're currently in beta testing for a first release, which we hope to release this year. We're beta testing with the European Weather Cloud. It exposes a REST API, and we will also provide then CLI and Python clients to aid users to use it. It will give you access to Mars if you have permission to do so, and we're also interested in implementing Hypercube data access later in the project, so probably in 2021. So it's typical REST type of interface. You'll have a retrieve similar to the retrieve that we saw earlier. So if you've used ECMWF, the Web Mars in the past, it's essentially going to be a very similar type of a request. It'd be asynchronous, so you can submit your request from the client to the Polytope server, wait some time, and then poll for status. You can list requests and then poll, and we'll tell you not yet available, depending on either it's processing, you're in a queue, or the data forecast data is not yet available. When the data is available, you get it back. You can delete requests and so on. In terms of the system design that we've implemented, so a key point for us was scalability, and particularly that the architecture will be elastic enough for us to scale easily. So we want to have like multiple front ends, multiple workers on the back end, and so we can scale depending on demand as we add more users. Ease of deployment, so we have Kubernetes support, and then a shallow software stack as well. So we have our front end here, say Polytope ECMWF.int of our REST API. We have then the various parts of the architecture, such as a request store, broker, queue. At the moment, we're piggybacking on open source software as well, which we're grateful for. So the request store at the moment is MongoDB, the queue is RabbitMQ, the front end is Flask, but the infrastructure is generic enough that we can plug and play as we wish. We have a worker pool, and then a worker pool on the back end will then go visit the various data sources and check if the user has permission to access those, and then fetch the data either from the FTB immediately after or soon after it's been produced from the forecast, or go to the Mars archive, or go to another data source. So we then stage the data in the data staging area, and then the user can come poll and get the data when it's available. So thanks for your attention, and I'll take any questions if you have them. This one, or?
Yeah, I think that one. Okay, so I think you mentioned that you were moving 30, was it terabytes or?
Terabytes at the moment, yeah.
What tools are you using to push that around as far as protocols go?
Yeah, so I'm not familiar, I don't know what we're using at the moment in terms of I think just FTP or...
Is a push system, so we deliver directly to
Are you doing that like over multicast or?
So some of them are using standard FTP, some are using S3
Yeah, I think it's mostly FTP, but there's also S3. But I mean, what we're talking about here is not to replace. So the model we're building at the moment, we would still have our dissemination system pushing that 30 terabytes. We'll still have users coming to us via the Mars archive, via the Mars Web API for the moment. But this is then the third option, which will allow us users to come to the cloud and access data via that. So it's not necessarily, it'll be a parallel system to the dissemination system.
Yeah, it's usually difficult to push out that amount of data, so I was wondering if you guys are using grid FTP or something like that.
Yeah, we have a colleague who we could put you in touch with, our colleague who's
okay.
dedicated to that. But we are pushing 30 terabytes, and at the moment, I think the limit we have on that is we could go up to 40 or 45. So yeah, it's a significant amount of data disseminating globally. The only issue then is within the next 5 or 10 years, that will increase by an order of magnitude, potentially. So we have to think about new ways of bringing users to the data rather than pushing it and so on.
And do you want to make, for example, Polytope available as open source, or is it already available?
Yeah, I mean, making this, I think the plan is to make it open source. I mean, it's sort of limited in terms of, I mean, you need access. It's sort of built for the Mars archive, and I mean, what we will make open source is the Python clients that we mentioned. So similar at the moment, the link that I showed you for the Web API, that's on PyPI. You can access that, and you can use that then for WebMars access. And so we will similarly make it available on PyPI. And so the command line interface and the Python client will be there. And I think probably the code will probably also be there in general. I don't think there's any reason for it not to be. But yeah, it's kind of limited. Yeah, but it's there if there's interest. Yeah.
You mentioned moving compute to data. How would that work in practice if I write a Fortran program that requires Python 2.5 and stuff like this? Would I have to push it in a container and give the container to you, which uses the data?
Yeah, I mean, I think at the moment we're just supporting this Python at the moment, so that Python interface that we showed for the CDS. And then as time goes on, we may, I think with Polytope that we're developing, we may start considering developing or supporting more complex, so containerization, such as that. But we're not quite at that point yet of development. So I'd say that's probably maybe about a year or so away.
And is that part of Polytope, or?
Potentially, yes. Yeah.
Okay.
In the beginning, you mentioned that you use Lustre. What do you use as backends?
How do you mean, sorry?
The backend for the Lustre file system, is it ZFS? Is it something?
So it's just POSIX at the moment, but we're investigating Ceph and also MVRAM in parallel at the moment. But it's POSIX currently, and we have some projects or some investigation for looking at the Ceph. Yeah.
And what was the reason for choosing this file system?
So I think it was just for historical reasons, or I think that's what was mostly available at the time. So pre-Ceph, pre-MVRAM.
Okay. Someone else?
Why you choose Bologna? I like the choice because I'm Italian, but it's just curious.
I don't quite. I mean, possibly for political reasons, and one of the issues was to make ECMWF a multi-site organization, so not to simply just have the HPC located in Reading in the UK. And so then there was a process then to choose where it would go, and so member states then were free to submit proposals and submit applications a few years ago, and then ultimately then Bologna was chosen for site for various parameters.
Thanks.
Yeah, looks like this was the last talk. Thank you, John.
Thanks
for this great talk.